We're back with another MCAT Max walkthrough. We're going to be looking at a passage from Jack Westin on blood pressure regulation. It's going to have some physics involved in it. So let's go ahead and take a look. So it says here that the heart alternates between phases of systole and diastole. So what is systole and diastole? So diastole is when cardiac muscle relaxes, the blood outflow valves close, and blood passively fills the heart. Diastole is when the muscle contracts, the valves open, and blood is actively ejected by the left ventricle into the aorta, and then into systemic circulation. So let's look at this diagram and kind of figure out what that means. So remember, the heart is divided into two parts, the right part and the left part. So what's actually on the left of you is considered the right part of the heart, and what's on the right is considered the left part of the heart. So this top part up here is called an atrium. The bottom part is called a ventricle. So we have a right atrium, a left ventricle. So what the ventricle is going to do is it's going to pump blood. So the right ventricle pumps blood to the lungs for it to get oxygenated, whereas the left ventricle is going to pump blood to through the aorta to the rest of the body. This blood is coming back from the lungs. This blood is coming back from the lungs, and it has oxygen in it, so it's getting pumped to the rest of the body. So what is diastole? Diastole is that part where blood is filling the ventricle. So the muscle, this ventricular muscle is relaxed, so blood is just seeping in, coming in. Whereas systole is where this ventricular muscle is contracting, and it's creating a higher pressure area. So it's like pushing the blood, ejecting the blood out of the heart. So in the right ventricle's case, it'd be ejecting it to the lungs, whereas the left ventricle is pushing it to the aorta. Okay, so that's what systole and diastole is. So it says the driver of blood flow is a pressure gradient between high pressures generated by the left ventricle and the aorta. So the left ventricle, the aorta, they're creating high pressure. And remember, things always flow from high pressure to low pressure. So it's pushing that blood throughout the body by creating an area of high pressure in here, the left ventricle and the aorta. And the low pressure is where it's moving to. It's moving to eventually the veins, which are returning blood to the heart. So the veins are going to have low pressure. And then here it tells us the blood can act similarly to water. So it gives us the density of blood, which is going to be important later on when answering these questions. So whenever they give you an important value in the MCAT, like a number, you want to kind of make sure you know where that is. So when you answer the questions, it'll come in handy. So here it tells us that mean arterial pressure, which just like means blood pressure, is measured at the brachial artery, and it's located in the upper arm. Okay, so this is what usually, when you measure blood pressure, this is what you're usually measuring. And it gives us a formula for blood pressure. So it tells us that it's the sum of the pressure during diastole and 1/3 the difference between the systolic pressure and the diastolic pressure. And that blood pressure is also equal to cardiac output, which is the flow of blood throughout circulation, and vascular resistance. Okay, so and they give us that formula here. So diastolic pressure plus 1/3 the difference between systolic and diastolic pressure equals mean arterial pressure, which is also equal to cardiac output, which is just flow through the heart and through circulation times resistance, systemic vascular resistance. So it says here that it's important to note how each vessel type contributes to the pressure gradient. So it says the arterioles are responsible for the greatest drop in pressure. What you want to know is that whenever something causes the greatest drop in pressure, whenever a vessel does that, that means it has the greatest resistance. Because if you look right here, this is flow. This is known as flow, cardiac output. This is known as resistance. This is the pressure gradient. Whenever something's resistance goes up, the pressure gradient is also going to go up. So when it's saying it has arterioles have the greatest drop in pressure, that also means they have the greatest resistance to flow. And it says here, despite their small size, the total cross-sectional area of the capillaries is quite large. And they contribute a relatively minimal drop in pressure, because even though you think of capillaries as like a small vessel which blood is flowing through, so remember, the smaller your radius is, your R is, the greater resistance you'll have to flow, right? Because less blood can't flow through a smaller hole, you know? So you would think the capillaries, being the smallest vessels, would have the greatest resistance and the greatest pressure drop. This is wrong, because the area of the capillaries, like the area of the tubes, all add up. So they're actually not that small it's not actually that small of a hole for the blood to flow through. So there's not as great of a drop in pressure. So there's not as great of a resistance. And it says the larger diameter and relative inelasticity of the venules and veins ensures their contribution to the pressure gradient is negligible. So because the veins and venules have a larger diameter, they have less resistance and less pressure drop. Okay. So let's attack the questions. So it says the pressure remains constant. Which of the following would lead to the greatest increase in bulk flow rate through systemic circulation? So this question is asking about flow. So what is flow in this equation? This is flow. Cardiac output is known as flow. Whereas this is resistance. And this is our pressure gradient. So we know that change in pressure equals flow times resistance. So we want to solve for flow. So if we just rearrange this equation, we can see flow is equal to the pressure gradient divided by resistance. And resistance is equal to, so this is something you're going to have to memorize for the MCAT, 8NL over pi r to the fourth. Where r is the radius of the tube. So this is an exponent. R is the radius of the tube. Pi is the constant pi. N is for viscosity. L is for length. So since r is in the denominator, we need to flip this. So we get change in pressure equals pi r fourth, or change in pressure times pi r fourth over 8NL is going to be equal to our flow. So we can get the answer really easily because we see that the radius is being raised to the fourth power. Any effect on the radius is going to be magnified because it's going to be raised to the fourth power. So if I double the radius, we raise that whole thing to the fourth power. That's going to be your original radius to the fourth times 16. So you're going to have your 16 times the original value. So any multiplication of the radius is going to cause a greater change, like based to the fourth power. So we're gonna say doubling the vessel radii will cause the greatest increase in flow. So I multiply the radius by 2, you raise it to the fourth power, it's gonna be 16 times the entire flow, right? Whereas if I quarter the fluid viscosity, so you quarter the fluid viscosity, it's gonna be 1/4 in the denominator, which is gonna be equal to 4 times the total flow. That's not as much as 16 times the total flow. And we double the blood vessel cross-sectional area. That is not going to have as great of an effect as the radius. And doubling the length, if you double the length, you'll have 1/2 the flow. So that actually decreases the flow. So B is our correct answer, because doubling the vessel radii, you're raising it to the fourth power, you'll have 16. So whenever you'll get a lot of questions in the MCAT asking you about what is going to cause the greatest change in the flow rate, and then you use this equation. This is flow pressure gradient times pi to the fourth over 8 NL. And whatever option has like increasing the radii, that's going to increase the flow the best, because it's being raised to the fourth power. Let's move on to the next question. It says a man has a heart rate and stroke volume of 60 beats per minute and 60 milliliters per beat. His systolic pressure and diastolic pressure are 120 and 80 respectively. Which of the following is approximately systemic vascular resistance? So what they're doing is they're asking us to use this formula down here. So what you need to know is that cardiac output is equal to your heart rate times your stroke volume. So stroke volume is the amount of blood that your heart pumps out with each beat. So if we know the beats per minute and we know the volume pumped out per beat, that gives you your volume per minute. So we want to multiply our heart rate, 60 beats per minute, by our volume per beat, which is our stroke volume. So this is stroke volume. This is heart rate. So multiply that out, you're going to get 3,600. So our cardiac output is going to be 3,600 milliliters per minute. Okay, good. And we want to solve for our vascular resistance. So our systemic vascular resistance, right? So we need to know our mean arterial pressure, right? So they give us our systolic and diastolic pressure, and we can use that in this equation to calculate our mean arterial pressure. So our diastolic pressure is 80. And we do 1/3 times our difference. So the difference between systolic and diastolic is 40. So that's going to give you 40 over 3 plus 80. So what I like to do is convert to fractions. So that's going to be 240 over 3 plus 40 over 3. Yeah. So what that's going to do is that's going to give you, let's see. That's going to give you about 280 over 3. And we know this is approximately equal to 270 over 3, which we know is about 90. So we know that's 90. So that's pretty similar. So we know our mean arterial pressure is 90, right? So we know 90 equals our cardiac output, which is 3,600. And our SVR is unknown, right? So we divide 90 by 3,600, which is 1 over 40. Which is, so we know 1 over 20 is going to be So we know 1 over 20 is 0.05. One over 40 is going to be half that. It's going to be 0.025. Okay, so our answer is going to be 0.025, and you want to make sure you want to make sure your units are always good throughout this. So you want to make sure, so we have minutes, we use milliliters, and yeah, and our mean arterial pressure, we use millimeters of mercury. So we should be good with units. So that's the correct answer. Let's move on to the next question. Assume the circulatory system of a 1.8 meter tall man can be modeled as an ideal hydrostatic column. His blood pressure is reported as 117 kPa when taken in the upper arm, 1.4 meters above the ground. What pressure will be measured in the man's foot? So let's draw a man. Okay, this is just a stick figure drawing. He's got arms. This is his legs. This is his arms. Okay, so we know the pressure in his arm right here is 117 kPa. His arm is, ask what the pressure in the man's foot is. His foot is going to be 1.4 meters below his arm. So it's going to be whatever pressure, the pressure formula is the pressure at the point you're starting at, so atmospheric pressure usually. But we're just going to say the pressure at his arm plus the depth, so density, which is P, times G, the gravitational constant, times H, which is going to be the depth. So the depth between his foot and his arm. So his foot is considered 1.4 meters below his arm. So the H is going to be 1.4. And the pressure above his arm is 117. So we want to add 117, the pressure from above his arm, to the pressure 1.4 meters deep below his arm. So that's going to be 117 plus the density. Remember, I told you to pay attention to this. The density plus 1060. So 1060 kg over meters cubed. Gravitational constant, which is going to be 10 meters per second squared. Times 1.4 meters. Okay, that's kind of squished together, but so if we multiply all that out, 14 times 1060, we're going to get something about, it's going to be equal to approximately like 14 So 10 times 1.4 is 14. 14 times about 1,000, so that's going to be about 14,000, right? So we're going to get 117 plus 14,000. But again, we have to pay attention to units because they're asking kPa. So when we multiply these units out, meters cubed, meters canceled. So you get meters squared actually here. So meters squared divided by meters cubed is going to give you kg per meters second squared. That is the unit for Pascal. We want in kilopascal. So you need to memorize this, that kg over meters per times second squared is the unit for Pascal. So we have 14,000 pascals plus 117 kilopascals. So that is 117 kilopascals plus 14 kilopascals. That is about 131. So this is PA. So this is 14 kPa. 117 kPa plus 14 kPa. It's going to be 131 kPa. So that's going to be the answer to our question. So whenever they ask you for a pressure in a tube question, you want to first find the pressure at whatever point you're starting at. So that will be your P, usually your atmospheric pressure. And then if it's asking you the pressure at a certain height below it, you want to do PG, so density times gravity, which is 10 on the MCAT, times the depth of the point you're looking at. So the point you're starting at, whatever pressure is there, plus PGH, where H is the depth, the distance between your starting point and whatever point you're looking at, whatever point they're asking the pressure for. So your answer is 131 here. On the next question. Angiotensin II causes global vasoconstriction. Assuming constant blood pressure, when angiotensin II is injected into the body. So vasoconstriction, if you have a smaller radius, so you have a shorter circle, tube, you're going to have more resistance to flow, right? So resistance to flow is going to increase. And when your resistance to flow increases, less blood is going to flow through this tube, right? Because it's smaller, right? Less blood is going to pass through. So we know it's not going to increase. We know flow through the pulmonary circuit, flow through the systemic circuit is not going to increase, right? Because this radius is getting smaller, less blood can flow through. So 2 and 3 are false. But 1 is right, because right, we have more resistance to flow because the radius is getting smaller. So the correct answer should be 1 only. Okay. Let's make sure that, yeah. Based on the following paragraph, the greatest contributor to vascular resistance is. So remember, the greatest contributor to vascular resistance will be the vessel that causes the largest pressure drop. Remember we talked about it? Largest pressure means largest resistance means largest pressure drop, right? Because the resistance is pressure is proportional to resistance. It says here arterioles are responsible for the greatest drop in pressure. That must mean they have the greatest resistance. So I want to say arterioles. All right, guys. Let's see. Let's make sure we got everything correct. Yep, correct. 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 Incorrect. All right, great job, guys. Make sure to check out the MCAT Max website to check out social media, and also feel free to sign up for tutoring on the website or contact us via social media. We're offering free group tutoring and individual tutoring to everyone. So thank you.